Okay, we're still pursuing our goal of finding the area under a graph of any function between any 2 points. So this area right here is our goal under a function f of x from point A to point B. So far all we've done is estimate that area using rectangles, either left or right or midpoint, and then we learned about trapezoids, but none of those were really great. Some of them could get pretty close, but we need to eventually make this the perfect area. So we're not going to learn how to do that for any function yet, but we're going to start to discuss situations where we can find the perfect area. So let's just start with some symbols. This symbol right here is called a definite integral. This symbol is it's kind of an elongated S. This is the integral symbol. The A on the bottom and the B on the top tell us where we're going to start and where we're going to stop accumulating the area. And f of x is the function, of course. So this symbol stands for this area. If that area happened to be 7 units squared, then this integral would equal 7. That's what that symbol means. It is the area. Now, there's a couple of assumptions. When you say the area from A to B, it is assumed that we're moving left to right. If you move right to left, then something kind of strange happens, because in geometry you learned that area can never be negative, and that just makes sense. But we are going to allow integral values to be negative if we're moving from right to left. So the integral is negative. It's not truly a negative area, but right to left just means negative. So it's kind of, that value would be negative. So one way to write that, if this were 7, the integral from B to A, that's what I mean by moving right to left. I'm just switching which number's on top and which number's on the bottom, would be -7 if you're moving right to left. Also, if you are below the axis, then the integral is also negative. So again, that doesn't make sense to have a negative area, but if you had a graph that was down here, moving from A to B, and let's say the area is 5 down there, the integral from A to B of f of x would be -5. So the only exception to this rule where we have just an area, integral from A to B is area, is moving right to left, and if that graph is below the axis, those would produce negative values of the integral, not truly a negative area, but the integral itself would have a negative value. All right, so for now, the only f of x's that we can use are ones that create graphs with geometric shapes that we're able to find areas of. We haven't learned how to just use a sine or an x squared plus 2 or any other function and find the area under that. That's what's coming next. For right now, just to study integrals themselves, let's talk about some areas that are made by geometric figures. So this function, it's a piecewise function made out of 3 pieces, and you see 2 semicircles and a triangle. So these are areas that we can find, which is going to allow us to practice some of these rules. This first little triangle would be 1/2 times 5 times 2.5, and that's going to be an area of 6.25. The first semicircle that goes from -5 to 5, that's half of a circle of radius 5. Area is pi r squared, so that would be 25 pi. So let's just call this 12.5 pi, just to have something that's pretty easy to work with. This green semicircle is half of a circle of radius 3, so the full circle would be 9 pi. So let's just call this one 4.5 pi. The point is that these are values that I can calculate using geometry. And so if I want to know the area under a graph from point A to point B, then I just use the geometric formula. And this will let us practice those rules. So the integral from 5 to 11. So this right away tests us out on one of those rules. Moving from 5 to 11, I'm finding this area right here. And since it's below the axis, I know that this is a negative amount. So the integral from 5 to 11 is just -4.5 pi. All right, the integral is negative, the area is positive, but because that area is below the axis, I give the integral a negative value. The integral from negative 5 to 11, so that's going to include that area we just found plus this area. Now, if you're integrating and you have some area above and some area below, those two things are just going to cancel each other out. So 12.5 positive and 4.5 negative makes 8 pi. All right, that 8 pi was 12.5 pi minus 4.5 pi, which gave me a total of 8 pi. So whenever you have area that's above and below, that area that it's above is going to cancel out that negative area which is below, and whichever one's bigger, that's going to be the sign of your answer. Okay, next, negative 5 to 5. So that's just straightforward 12.5 pi. All right, that's above the axis. We already found the area ahead of time. So moving, excuse me. Take that back. The area from 5 to negative 5, I wasn't paying attention to my own question. From 5 to negative 5 is moving from right to left. So let's make that negative 12.5 pi. All right, moving right to left makes it negative. All right, next question is from 5 to negative 10. Now that's moving right to left, but going all the way to negative 10. So here's something interesting that happens. We've got kind of a double negative going on. If you're moving right to left, that makes the area negative. If you are below the axis, that makes it negative, but those two things combined make it positive. So from 5 to negative 10, I'm going to get negative 12.5 pi, which we had on the last problem, and then I'm going to add to that 6.25. And you might say, well, that's below. Why is it not negative? Well, it's not negative because it's below, and I'm also moving right to left. Two negatives make a positive in this case. Okay? Negative 5 to positive 5. There's the one that I was doing earlier. Negative 5 to positive 5. Oh, okay, and that's 2 f of x. This brings up a new rule which says if you have a constant on your function, that can just kind of hang out, just like it did in a derivative. You can, in fact, move it to the outside. And all that's going to do is double our answer. From negative 5 to 5, the integral is 12.5 pi. So double that, 25 pi. It's probably what you would guess would happen, but just to confirm what you were thinking, 25 pi, just double it or triple it or whatever that constant is if there's a constant inside. All right, negative 10 to 11. So that's the full area, but it is absolute valued. So all an absolute value does on a function is make its mirror image above the axis if it's below. If it's above the axis, then it doesn't do anything to it because absolute values of positives are just those numbers. So this one's going to be positive 6.25 plus the other two circles, all positive now. So 12.5 and 4.5 makes 17 pi. So 6.25 plus 17 pi is my area of the absolute value. And the last one, which is just this rule is always listed, but it doesn't really, it's kind of just intuitive. The integral from 5 to 5. If you don't have any space, then you don't have any area. Okay, you don't have any room, any change in the x to accumulate any area. So anytime these two numbers match, you just say that's 0. Again, probably what you would think, but just to confirm. All right, so our goal to find some perfect areas, we found those. They are only things we can do at this point if the graphs create geometric shapes of which we can calculate the area. But this is more about this symbol, the integral symbol, what it means, and these special rules like below the axis, right to left, etc.